In this lecture, I am going to talk about Newton's method, which is one of the most well-known numerical methods for solving root-finding problems. But first, let me say a couple words about one of the most famous and brilliant scientists of all time, Isaac Newton. Sir Isaac Newton was an English mathematician, physicist, astronomer, and philosopher. He is widely recognized as one of the most influential scientists of all time. One of his most famous books, Mathematical Principles of Natural Philosophy, was published in the end of 17th century, and it established classical mechanics. For example, in this book, Newton formulated such famous laws as the laws of motion and laws of universal gravitation, which all of us studied in high school. Also, he made an important contribution into celestial mechanics and optics. He was one of the pioneers who built practical reflecting telescope, and he developed theory of color based on his experiments with prism, which separated white light into the colors of the visible spectrum. But today I'm going to talk about his contribution into numerical analysis. Although he described his numerical method only for polynomials, it can be applied to a broader range of problems. First, let's briefly recall how this method works for one-dimensional case. Recall that Newton's method is a recursive algorithm for approximating the root of a differentiable function. Suppose what we want to approximate the solution to fx equals 0, where fx is a differentiable function. Assume that we selected initial approximation x0. Of course, arbitrarily. So, to approximate the root, we supposed to use the following recursive formula, where n greater equal to 1, and function g has the following form. Phi is another differentiable function, and derivative of x doesn't equal to 0. Then, for the iterative procedure derived from g to be quadratically convergent, we need to have the following condition, and derivative should be equal to 0 when fp equals 0. And just to remind you, when p is a solution of the following equation. So, it's possible only in case if phi equals 1 over f prime p. Now, if we let phi x equals to 1 over f prime x, of course f prime doesn't equal to 0, so we will ensure that this equality holds and produce the quadratically convergent procedure. our recursive formula will be following. If now value of function at p equals 0 and f prime p doesn't equal to 0, then for starting values sufficiently close to p, Newton's method will converge at least quadratically. So this is a Newton's method for one-dimensional case. Now let's consider n-dimensional case where we have matrix A, every element of which is a function from n-dimensional real-valued space into one-dimensional real-valued space. And matrix A should be such that the following expression gives quadratic convergence to the solution of this equation. Of course, matrix A should be non-singular matrix at the fixed point P of a vector-valued function G. And let me just remind you that P belongs to our domain, where domain is a subset of n-dimensional real-valued space. And just to remind you that non-singular matrix, the definition is following. N by n, matrix A is said to be non-singular or invertible if n by n inverse matrix exists with the property that product of matrix A and inverse matrix equals to the product inverse matrix and A and equals to identity matrix. Now let's recall one-dimensional case again. We formulated the following theorem. Let P be a solution of the equation x equals to gx. Suppose that first derivative of function g at P equals to 0 and second derivative of g is continuous and bounded by certain constant capital M on an open interval I which contains P. Then exists delta greater than 0 such that for any initial approximation P0 from the interval P minus delta P plus delta, the sequence defined by the recursive formula when n greater or equal than 1 converges at least quadratically to P. Moreover, for sufficiently large values of n, the following inequality holds. Now let's generalize this theorem for n-dimensional case. In n-dimensional case, we can formulate the following theorem. Let P be solution of the equation gx equals x, where gx is a vector-valued function and x is vector. And suppose exists constant delta greater than 0 with the following properties. Every partial derivative of function g is continuous on the certain set and delta, where norm of vector x and p less than delta for each I and j from 1 to n. Second, every mixed derivative is continuous and bounded by certain constant m, whenever x belongs to that set and delta, for each I, j, and k from 1 to n. And the third property, that partial derivative at p equals to 0 for each I and each k from 1 to n. Then exists delta hat, which is less or equal than delta, such that the sequence generated by the recursive formula, this one, converges quadratically to the solution P for any initial approximation, which means x0 can be chosen arbitrarily. Moreover, L-infinity norm between the difference of kth iteration and the solution less or equal the product of a certain constant and R squared L-infinity norm between previous iteration k minus 1 and actual solution for each k greater or equal than 1. Let me explain how this theorem works. So we have matrix A n by n, where every element is a function from n-dimensional real-valued space to one-dimensional real-valued space. Also, we assume that matrix A is non-singular near solution P of the equation fx equals 0. So, what we have here is a vector form of our equation. This function g is a vector valued function. And we can rewrite this vector form in a component form. So functions gi are component functions for function j. We also have function f, which is also a vector valued function, and functions f are component functions for function f. We also have here inverse matrix. And b, I, j are components for this matrix. So, theorem states that we should deal with partial derivatives. Now we can take equation star, this one, and take derivative over all xk. This is how we can get system of equations. Let's see 2 stars. Theorem implies that partial derivative at solution P for every xk should be equal to 0 for each I and each k. If we consider first case I equals to k, we can consider first expression here. This one vanishes, and this is what we can get, this equation 1. If we consider I doesn't equal to k, we consider second expression, then we will get this equation 2. In order to rewrite our first and second conditions from the previous slide in a vector form, let's recall what the Jacobian matrix is. The Jacobian matrix of a vector valued function in several variables is the matrix of all its first order partial derivatives. In the literature, it's simply mentioned as Jacobian. The Jacobian matrix represents the differential of function f at every point where f is differentiable. Then conditions 1 and 2 from previous slides require that this equality holds where I is identity matrix. As a consequence, the next inequality should hold. And hence, the appropriate choice of matrix A is simply Jacobian, because it satisfies the third condition of our theorem. Then function g is a vector-valued function which is defined as follows. And in this case, the functional iteration procedure involves selecting x0 as our initial approximation and generating for k greater or equal than 1, and this is our recursive formula for that method. So this method is called Newton's method for nonlinear systems. So usually Newton's method for nonlinear systems gives quadratic convergence. Of course, we expect that we have initial approximation which is good enough. Which means it's sufficiently close to our actual solution. And we assume that inverse matrix for our Jacobian exists. So at every step we have to compute Jacobian and its inverse matrix, so which is computationally expensive. In order to avoid it, in practice use so-called two-step technique. First step, we find vector y which satisfies this equation. And at step 2, we compute xk by simply adding this vector y to previous k minus 1 iteration for x. So let's see how Newton's method works using an example. Solve the following nonlinear system and find all solutions. Assume that we have two equations and two variables. Our vector x has two components, and x and y. And first, let's just simply plot our equations. We will see that we have a unique solution at 1, 1. So this is our exact solution. So now let's transform our system into vector form and define component functions f1, which is minus 1 minus 1, and x, y plus 2. And our vector form will be using component functions. This is our vector form. So first we can, this system is very simple and we can use a built-in program. For example, for MATLAB, it can be fsolve. We simply plug our function, we choose initial approximation, and we can get solution. This is how built-in program works. Now let's implement Newton's method. So this example I'll show you how to solve using computer. So we defined component functions f1 and f2. Now we have to compute the Jacobian. The Jacobian matrix will look like following. So we remember that this is matrix which consists of first order partial derivatives. So let's take partial derivative of f1, and it will be this one. If we take partial derivative over y, it's 1. Then for function f2, we take derivative over x first, it's minus 3, and y, it's 3y squared. This is our Jacobian. Then we will use again MATLAB to see how Newton method works. So we have our function. We define component function f1, f2. We have initial guess. Initial guess or approximation. We have differential. This is our Jacobian. And actually the simplest possible formula for Newton's method. So in 5 iterations we can achieve very accurate result. So this example was very simple and I showed you how it works using MATLAB. Now let's consider more complicated example and let's do it manually and compute everything by hand. Now let's solve more complicated system. Apply Newton's method to the nonlinear system where we have 3 equations and 3 variables. Before we start actually solving the system, we should define vector valued function f and its component functions. Just to remind you that f1, f2 and f3 are component functions. We simply equate left-hand side from each equation to f1, f2 and f3. Once we finished, we should start compute Jacobian. Jacobian, this is a matrix of first partial derivatives. We should compute partial derivative of all functions for each function f1, f2, and f3 in our case, at every point where each function is differentiable. For example, how to get 3 here? According to the definition, it's df1 dx1. We look at the first equation and simply take partial derivative over x1, which equals to 3. So, this first line, it's f1, f2, f3, and here we take derivative over x1, derivative over x2, and derivative over x3. As soon as we are done and we constructed our Jacobian, we should compute our initial approximation. And we should recall that our x0, 0.1, 0.1, and minus 0.1. We plug into our system, and this line, this is what we can get. Once we got the Jacobian and values for vector valued function f, we can plug our initial approximation into Jacobian and compute it explicitly. Then I mentioned before that instead of computing inverse Jacobian matrix at each step, we will do it differently. First step, we solve this system to get y0. And the second step, in order to get the next approximation for x, we simply add our previous approximation for x and this y0 what we just found by solving this system. Then, continuing with k2, 3, and so on, we can get this sequence of values. And with yk, also you can get from solving linear system for every iteration. Finally, at kth iteration, we're supposed to solve this system. Where j is our Jacobian, what we take from k-1 iteration, and every x should be taken from k-1 iteration. Vector y also we take from k-1 iteration, and vector valued function f also should be taken from k-1 iteration, and every x should be from previous iteration. Below the results, where we can see first line, it's our initial approximation, and we can see that in order to achieve good accuracy in L infinity norm, we need just 5 iterations. And we see that Newton's method in this particular case converges very rapid, and we can say that our initial approximation is sufficiently close to our actual solution, which means that we have good initial approximation. This is all example is solved.